So, you've run the standard, and you should have gotten something that looks like this. If you look down here, you have a chart of all of your absorption readings. They're laid out in the same pattern as your plate. Now, I've gone through and cleaned up the data a bit, so we can analyze it better. First thing you want to do is take the average of all of the columns. Once you have that, then you need to calculate the number of micromoles of the 4-nitrophenol you have per well. To do this, recall that we did a dilution of the standard solution. This took the concentration of 20 millimolar down to 2 millimolar. Knowing this, we can calculate the number of micromoles we have by converting the number of microliters we have in a well to liters, and converting 2 millimolar of the standard solution to molar. Once we do this, we multiply the two together to get the number of moles we have in the well. We then can convert it to micromole per well. Now, all we have to do is graph the number of micromoles of 4-nitrophenol on the x-axis and absorption on the y-axis. This gives us a graph that shows the relationship between 4-nitrophenol and its absorption. But the more useful version of this graph is the inverse. This graph tells us the amount of 4-nitrophenol needed to get an absorption of 1. We will later use this to convert the absorbance of the test to the rate that 4-nitrophenol is produced per minute in micromoles. Now that the standard is done, we can start processing the data from the test plate. When the TECAN finishes, it should make an Excel sheet that looks like this. There's a lot of data here, so to make it more manageable, we're going to add a column and convert the time from seconds to minutes. To do this, divide the time by 60. Next, we want to find the slope of all of our wells. You can do this by taking the slope command and putting the column of the well you want, and then the column of time in minutes. Remember to put the $sign on the column for the time before you copy the equation, because this will ensure that Excel always refers to the correct column. Once you have done this, copy your slopes and paste just the numbers into a new sheet. Once I have the data into a new sheet, I like to organize it and label it so it matches the plate. Next, you want to take the averages of your slopes for each dilution. Now, you want to subtract the slope of the control from the rest of the dilutions. This ensures that the slope of the dilutions is unaffected by any 4-nitrophenol made from the buffer. After this, you want to multiply the slopes of the dilutions by the slope of the flipped standard graph. This will convert the slopes from the increase in absorption per minute to the number of 4-nitrophenol in micromoles produced per minute. That is also the definition for 1 unit activity. So now we have the raw activity for each dilution. There are only 2 ways to find the specific activity from here: single point and linear regression. The better option in this case is linear regression, but we will also go over the single point method, as it's helpful in finding the activity when you only have 1 dilution. To do the single point method, you need the amount of the stock in each of the dilutions in milliliters. This can be found by taking the number of milliliters dosed, in this case 0.95 milliliters, and divide it by the dilution factor. Next, we take the raw activity and divide it by the amount of stock. This gives us the relative activity of this dilution. To get this in terms of milligrams of enzyme, we take the previously calculated relative activity and divide it by the stock concentration. In our case, 3.5 milligrams per milliliter, but this may be different depending on your stock concentration. This gives us the specific unit activity for each dilution. You may notice that there is a variation on the activity between these different dilutions. When you have more enzymes, there is more competition for the substrate, so some enzymes are outcompeted and are able to react less with the substrate. This causes the average to be reduced. Now, to find the specific activity with the linear regression method, we need to find the milligrams of enzyme in each dilution. To do this, we take the stock concentration and multiply it by the amount of the dose in milliliters divided by the dilution factor. Now, all we must do is graph the milligrams of enzymes on the x-axis and the raw activity on the y-axis. To clean up the graph, we need to look at the absorbance over time. When we do this, we see that the 400 times dilution is very linear, while the 80 times dilution is somewhat curved. When running this assay, you want to have a linear curve for your dilutions. Knowing this, we can throw out the 80 times dilution. Also, seeing this data, if I were to repeat it, I would probably go to higher dilutions than 400 times. Probably starting at 400 times and going up to 2000 times dilutions. This would ensure that all the dilutions have a linear curve. Now that we have removed the 80 times dilution, we get a far better R-squared value. To get the specific unit activity, we need to take the slope of the graph. In our case, we get a specific activity of 0.15. This is what we got in this experiment, but that value may be different from yours, and that's okay. Enzymes can be fickle, and as such can vary in activity due to many different conditions. Thank you for watching this video. If you have any questions, we have an FAQ document in the description of this video. And thank you.